So we want to talk about graphing exponential functions. We have discussed in the previous section how to use the exponential equation to solve for things. So we did some exponential equations with half-life and with doubling. And we said we use this y equals ab to the t over p. That was kind of what we use as our base formula. And what we're going to do is we're going to change it slightly. We're going to call the base c. And the reason we're going to do that is just because we're going to use parameters a, b, h, and k. So we're going to use b for another purpose. So for what we're doing in terms of graphing exponential functions, we're just going to change it so that the base is going to be c because we use b for other things in graphing and not just for exponential functions. We use it for a whole host of functions, sine and cosine and tangent and all the trig graphs, radical functions, rational functions. So b's kind of already used, but generally speaking, we're going to look at exponentials of the form b to the x, a base, which we are going to now call c. So that's where the c to the x is coming from. Okay, hopefully that makes sense. And really what we want to know is, first of all, what does the sort of basic graphs look like? What does exponential growth look like? What does exponential decay look like? So we've solved equations that have solutions to figuring out how much something's going to be after a certain period of time if it doubles every so often, or how much there's going to be if it decays by a half-life of 5 minutes or whatever. But we never actually looked at it visually. So that's what we're trying to do now. We're trying to graph them. And we just want to look at, first of all, the very basic function. Now, you can look at any base. I've just chosen 2 because it's a simple base. 1 would be the simplest base, but 1 isn't really an example of exponential growth because if you multiply 1 by itself however many times you want, you're still going to have 1. So this is the smallest base. 2 is the smallest base of exponential growth. And they look like this. They have this sort of shape to them. All exponentials do. Okay. Now, they have a horizontal asymptote at 0, y equals 0. And that is something that you probably haven't seen before. But essentially what a horizontal asymptote is, it's a value that the function approaches, but never actually touches. Okay, now, obviously, when you're drawing it by hand, at some point, it's going to look like it touches. But it doesn't actually mathematically ever get there. And that's because when you have a knowledge of negative exponents, I think you know that if we have, well, you do know because we've talked about it, but if you have 2 to the negative 100, for example, that's 1 over 2 to the 100. Now 2 to the 100 is massively big, so you're going to get 1 over some really, really big number, okay? And when you have something over a really, really big number, you get a really, really small number, okay? However, it's still a number. It's not 0, okay? It's going to be a really, really, really small number. Okay, that's really good mathematical terminology there. It's really, really small, but it's not ever going to be 0. So what the horizontal asymptote says is as you get really, really negative, and I'm talking a really big negative number, like minus 1,000, minus 10,000, minus maybe even 100,000, you're going to get a number that is very, very close to 0. Okay, it's not 0, but it's really, really close. So as x gets really, really negative, we're approaching 0. That's what it's saying. All right. The same thing happens with exponential decay. The only difference is that with decay, the shape is opposite. So it's going down to the right as opposed to down to the left over here. Okay. So there's still a horizontal asymptote at y equals 0. It's just as x gets really big because the 2 is already in the base. In the denominator. Okay. It's 1/2 as opposed to 2. So as x gets really big, 100, 1,000, 10,000, 100,000, you're going to have a really, really small number. So a couple of basic features. One is that horizontal asymptote. The other one is that you'll notice because they don't ever touch 0, they don't ever go negative either. And so the range is that y is just greater than 0, and also it means there's no x-intercepts. Okay, so those are 2 things that are important to recognize. And then the y-intercept for each of them is when x is 0, and if you raise anything to the 0, any base to the 0, you get 1, right? 2 to the 0 is 1, 1/2 to the 0 is 1. It could be any base to the 0. So this y-intercept of 1 is actually true of any base, okay, any basic exponential function. Now, we can move that around by adding in different parameters, and we're going to talk about how to do that. But as of right now, for a basic exponential function, regardless of what that base actually is, if it's 3 or 4 or 5, it doesn't matter, because anything to the 0 is 1, any base to 0 is 1, that y-intercept is always 0 and 1, right? And then the domain is x belongs to real numbers, and the range is y is greater than 0, because it never gets to 0 and never goes negative. That's why the range is y is greater than 0, and the domain is x belongs to real numbers, because you can take any power of that base. All right, so you can raise 2 to any number, and it will give you a value. So those are the basic features of an exponential graph. So if we were just going to draw one, let's say 4 to the x, what I want to do is this is going to be 4 to the minus 2, and then we're going to write that as 1 over 16. Okay, 1 over 4 squared. This is 4 to the minus 1, so it's 1 over 4. Then 4 to the 0. 4 to the 0 is 1. Then 4 to the 1, which is just 4. And then 4 squared, which is 16. Okay, so if I go 2, 4, 6, 8, 10, 12, 14, here's 16. And we're going up by 2's. And then my y will go up. Well, actually, let's go up by 1 on the x-axis, since that's what I'm kind of going up by for my x value. So let's go up by 1. We'll go up by 2 on the y, maybe. It's going to be cramped either way, because what happens is these numbers are really small, but these numbers that grow fairly quickly. So to put a scale on your y-axis is sometimes a little bit difficult, because it's just not, the numbers are so widespread. So what we'll do is we'll go up by 2's, let's say. So this is going to be minus 8 down here, and then 2, 4, 6, 8, 10, 12, 14, 16. There's 16 there. So I have minus 2, I'm at 1/16, so I'm sort of really, really small. Okay, minus 1, I'm at 1/4, still really, really small. At 0, I'm at 1. And then at 1, I'm up at 4, which is here. And then at 2, I'm already up to 16. Okay, and so you can see the shape is kind of like this. Go down like that, and it's going to continue down towards 0. So that's my graph. That's the basic shape. What is different in this context versus some of the graphs that you've drawn is, because it's exponential growth, it grows really, really quickly. So the x numbers, if you even choose like 4 or 5 or 6, you're already up into the hundreds, or even in some cases, depending on the base, up into the thousands. So it's really, you could say, well, I could pick any numbers. Yeah, you could, but it's really important you pick small x values if you're going to just do a table of values, because they grow really, really quickly, or they shrink really, really quickly if you're talking about decay. So it's really, most exponential graphs, I guess is what I'm trying to say, is it's really close to the x-axis that we're going to see anything. We're not going to stray very far from that, because when we do, the numbers get huge. All right, so these numbers, minus 2, minus 1, 0, 1, and 2, they are randomly selected in the sense that I can pick any x values, but I would encourage you that those are the values you want to use no matter what exponential graph you have, because those are the numbers that are close to the x-axis and therefore going to keep your y values relatively small, okay, in terms of positive powers, and relatively big in terms of negative powers, if that makes sense, because it's very difficult to draw, for example, 1 over 1,000 on a graph. I mean, how are you going to do that? So we keep the numbers pretty small in both directions, okay? So we're going to take the original function and we're going to try to do some transformations. Now, you would have talked about transformations a bit in grade 9. You would have talked about reflections and rotations and translations and dilations. So what we're going to try to do is we're going to try to move the function either up or down, left and right, and then we're going to stretch it out. Okay, which means instead of it looking like this, sort of the basic function, it might take a lot longer to stretch out. Okay, or it might go much more quickly, so it might go like this. All right. So there, in order to do that, there are 4 places that I can put what we call parameters. There's the option of multiplying a number in the front of C, and we're going to call that A. Okay. A does something to the graph. It's a vertical stretch. So it determines the stretch, meaning it determines how steep the curve is. So you've got a basic curve that I just drew, and then you've got that really steep one, a really long one. A is going to determine that. Okay, if it's negative, it's going to flip the equation across the x-axis. So if you have a negative a, what's going to happen is instead of your graph looking like this, which is going up, it's going to change and flip over the x-axis, so it's going to look like this. It's going to go down. Okay, so that's what we mean by a reflection in the x-axis. And again, you would have talked about reflections last year in grade 9. If you look at b, b up here is multiplying by x, so we can multiply it by the base, y. All right, that's the a value, or we can multiply it up here by the x. If we do that, we get the same thing. We get a horizontal stretch though, so it still affects the stretch of the graph, but the big difference is that if it's negative, it's going to reflect on the y-axis. So that means, just so you know what that looks like, if my graph is generally going like this, okay, and this is my y-axis, let's say, then it's now going to reflect in the y-axis, and it's going to look like this. Okay, it's going to come down, and it's supposed to be a mirror. That's not a very good symmetrical drawing, but you get the idea, hopefully. Okay, so it basically just flips around the y-axis. It reflects across the y instead of reflecting across the x. So that's what B does to the graph. H is a horizontal shift. Okay, so all it does is it moves the graph left or right. Now I've got a note here to remember that H is the opposite sign to that in the equation because it's x minus h. It's the same thing as quadratics. When you did a quadratics, you would have done something of the form this in terms of your vertex form of your quadratic equation. So it's very similar. So the h moves things left and right, and then the k value moves things up and down. It's your vertical shift. Okay. So what you're going to be tasked with is taking a graph, sorry, an equation, I guess, not a graph, taking an equation and looking at how does this look on a graph, and also what are the transformations? What's the vertical stretch, horizontal shift, vertical shift? And then how do those things affect the horizontal asymptote, the y-intercept, x-intercepts, and all of that? All right, so that's what we're going for. But let's look at a few examples. And as we do, we're going to look at some very important functions, or not functions, I guess. We're looking at exponential functions, but information about the graph, some features maybe is a better word of the graph. So things you're going to be asked to find. One of the things you're going to always be asked to find is the range and the domain. The nice thing is the domain is always, that should be an x. X belongs to real numbers. Okay, it never changes. So that's easy. That's a giveaway mark on any test or assignment. If you look at the range is determined by the k value. All right, it's either going to be greater than k if a is positive or less than k if a is negative. Okay, the y-intercept, you set x to 0, the x-intercept, you set y to 0. So you can solve those in either direction fairly easily. And then the horizontal asymptote is always y equals k. So you're going to be asked to state the transformations and then state this stuff. And that's how you find it. So everything is sort of situated with k, these two, and then these two are going to have a or b or h affect them, right, in terms of x-intercepts and y-intercept. The only time you're going to have an x-intercept, though, if you think about your graph, is if you move it down, because my general equation, right, the base to the x or c to the x always look like this, and this was my x-axis, right? So that means that the only way I'm going to have a graph is if either it goes down, okay, it flips, sorry, it doesn't flip, but it just moves down. So you can move it down using your vertical shift, or if it flips. So if it flips upside down, then this comes down like this, so there'll be an x-intercept. So there's not always, I guess what I'm trying to get at is there's not always an x-intercept. Sometimes there will be, but only in specific instances where you've either moved the graph down or you've flipped it. You've rotated it across, or reflected it, sorry, across the x-axis. So you're not always going to have an x-intercept. So the reason I bring that up is just so that if you are solving and you say this doesn't work, you don't get freaked out and think, well, then I must have done something wrong. It's possible that there's an x-intercept sometimes, but it's also not possible sometimes, right? So let's just look at an example of this. So we say apply transformations to sketch a graph. What's the vertical stretch? What's the horizontal stretch? What's the horizontal shift? And what's the vertical shift? Okay, we'll just look at that for now. So to do that, you're going to identify A, B, H, and K. A is right there, so A is 2. Okay, B is up here, it's multiplied by X, but there's nothing there. So if there's nothing there, it's just 1. H is right here, okay, because it's X minus H, it's X minus 4. So it's positive 4, so we're going to say it's 4 to the right. Okay, and then the vertical shift is at the end, but there's nothing here at the end, so there is no vertical shift. Okay, so you basically have to look at those A, B, H, and K values every single time. And it's really important that you recognize, and it's noted here, that the A value is only multiplied by the base after you've established the power to that base. In other words, you have to follow order of operations. So if I have, for example, if I say when x, let's say x is 2 in my equation here, and I say what's the answer, what we're saying is it's not 2 times 3 to the 2 minus 4. Okay, it's not taking 6 to the minus 2. That's not right. Okay, we don't multiply 2 by 3 and then raise it to the power. What it is 2 times 3 to the minus 2, and that is 2 over times 1 over 3 squared, so it's 2 over 9. Okay, so that's the difference, and that's what we're saying. So what we want to be able to do with all of this is say, okay, I want to be able to sketch a graph from an equation, and the way I'm going to do that is by identifying A, B, H, and K, knowing what they do to the graph, and then also using those to identify where the horizontal asymptote and the x-intercept, y-intercept, if there are those things, and then also draw the graph. So let's go through a whole example. All right, we've already done this part, 2, 3 to the x minus 4. We already know our 2, our 1, our 4, right, and then our 0. Okay, so then we go to our domain and range and all those things. So our domain is going to be, again, if we have a positive a value, which we do, then it's y is greater than k. So our domain, sorry, our range, I'm writing the wrong thing here. I'm going to move this down. Our range is going to be y is greater than 0. Our domain is always x belongs to real numbers. I wrote those in the opposite order. So our domain is x belongs to real numbers. Our range is y is greater than 0. Our horizontal asymptote is y equals k. In this case, k is 0, so it's y equals 0. The y-intercept we find by letting x be 0. So we go 2 and then 3 to the minus 4, okay, or 0 minus 4 if you want to write that. So it's 2 over 3 to the 4th, and that's 2 over 81. Okay, so that's our y-intercept. Our x-intercept, we can notice right away our range is that y is greater than 0, and therefore y can't be 0, so there are none. There's no x-intercept or x-intercepts. And then the last job that we have is to actually draw the graph. Okay, and to do that, what we're going to do, we're going to take our base. So our base is 3. You notice way back at the start, I told you that using -2, -1, 0, 1, and 2 for our x values is a good idea. So we're doing that here. All I've done is added 3 because the base is pretty small. So 3 cubed is just 27, so I can still handle that. Okay, but I'm using those x values, and then I'm finding the y value associated with the base that I have. So in this case, the base is 3. So that's where the 1/3, the 1, the 3, the 9, and the 27 are coming from. If you jump back, when we use 4, right, it was 1/16, 1/4, 1, 4, and 16. So the points that we're using to draw the graph, the thing is we're always going to use the same x values. We're going to use -1, 0, 1, 2, and 3. Okay? but the y values are just going to change based on what the base is. And the base is coming from way right here. This is where our base is, all right? So that's our base. That's what determines our original points. And then all we're going to do to find out where our new x value goes, we're going to take x, divide it by b, and add h. So in this instance, b is 1, right? And h is 4. So we're going to go x divided by 1 plus 4. And then we're going to take ay plus k. That's going to find us our new y. So our a is 2, so we're going to have 2y plus, and then k is 0. So all we're going to do is take each of these x values, and essentially all we're doing is adding 4. So minus 1 plus 4 is 3. 0 plus 4 is 4. And then 5, 6, and 7. So those are my x values. My y values, I'm just doubling them. So I'm going to get 2/3, okay, 2, 6, 18, and then 54. The other point that I know, okay, is up here, my y-intercept. So my y-intercept is at 0 and 2 over 81, which is pretty small, okay? But I know that point as well. So I've got to draw this graph. Now, I can go up by 1 on my x-axis pretty easily. 1, 2, 3, 4, 5, 6, 7. That's as far as I have to go. My y-axis is another story, and I was saying this earlier, and you can see, again, we have a bit of an issue with the numbers because the biggest number I need on there is 54. The smallest number I need is 2 over 81. So it's really hard to do that effectively. So I'm going to go up by 10, 20, 30, 40, 50, 60, because I need that 54, which is going to be right in there. Okay, the other ones then are going to be harder to place, but I'm going to start at 0 and 2 over 81. So that's essentially somewhere really close to 0. Okay, my next point that I have is 3 and 2/3. So there's 3. 2/3 is just under 1. So it's basically it's almost down because that's actually 10, right? So 2/3 is like down basically at the bottom. This is just a bit smaller. And this is the issue we run into with drawing these by hand, is it's really hard to get those numbers close at the start. Now, 4 is at 2, so we're up a little bit higher. Okay, and then we're at 6, so we're up a little bit higher, still trying to stay underneath 10. Then we jump to 18, so now we're here, okay, and then we jump all the way up to 54, so we go way up here. So our graph, it kind of traces along here and then slowly goes up and then it starts to grow. Whoops. Let me try to connect these a little bit better. All right, so there's my graph, and hopefully that makes sense to you. Okay. So let's look at another one, and then with those two examples, I will do maybe one more. But the video is getting a little bit long, but I want to show you just a couple more examples so you know what's going on. So vertical stretch, first of all, the vertical stretch is a 2. All right, the negative though means there's a reflection in the x-axis. So it's not, the vertical stretch is never negative, but you should state that there's a reflection in the x-axis. There's a horizontal stretch, the b value, there's nothing there, so the b value is 1. You notice the h value is going to be 3, but it's negative, so there's a horizontal shift of 3 to the left. Okay, because it's positive here, so it's negative when it comes out. And then the vertical shift is right here, it's -1, so it's 1 down. The domain is always x belongs to real numbers, so that's easy to find. The range, in this case, there's a negative a value, and the vertical shift is 1 down. So if there's a negative a, it's always y is less than k, so it's less than -1. The horizontal asymptote is y equals k, so it's y equals -1. The y-intercept, we're going to let x be 0. Okay, so we're going to get -2 onto 2 cubed minus 1. Okay, because it's 0 plus 3. You can write 0 plus 3 if you want to. So that gives me -2 times 8 minus 1, which is -17. So the y-intercept is 0 and -17. Okay, and then the x-intercept, because the range is y is less than -1, there are none. Because you need y to be 0. And we're saying y can't be 0 because it's got to be less than -1. So hopefully that makes sense, that process. Then when we get down here, Okay, we're going to use, again, you notice the numbers that I'm using, the x values are staying the same, -2, -1, 0, 1, and 2. Now they're 1/4, 1/2, 1, 2, and 4 because the base is 2. So 2 squared is 4, 2 to the 1 is 2, 2 to the 0 is 1, 2 to the -1 is 1/2, and 2 to the -2 is 1/2 squared, or 1/4. So then I'm going to try to do the new x by taking x divided by b. So we're going to take x, the x value that I have here, divide it by 1, and then add h, which is -3. So essentially we're going to subtract 3 from x. And the y, we're going to multiply y by 2, but -2 because the a value is -2, and then we're going to subtract 1. So -2 minus 3 gives me -5. All right, I don't need that bracket. And then the y value, I'm going to get -2/4 minus 1. Okay, that's -1/2 minus 1, so that's -3/2. Then -1 minus 3 is -4. These ones are easy, so I'm just going to do them all at once because they're just going up by 1. So -2 and then -1. All right. The 1/2 times -2, so -2/2 minus 1, that gives you -2. 0 and 1, now -2 times 1 minus 1 gives you -3. -2 times 2 minus 1 gives you -5. And then -2 times 4 minus 1 gives me -9. And then we could add in our y-intercept is 0 and -17. We found it up here. So we're going to try to draw that graph. So I'm going to put some axes down. And because all of my y values are negative, I'm going to just make it, actually, I'm going to have to do the same with I'm going to move my y-axis over some, okay? And the reason I'm doing that is because my x's are also all negative. So we'll do our x-axis fairly large in the negative x and not so much in the positive x. So we'll have x and y. Now, these ones we can probably go up by 1 in both. So we'll go 1, 2, -1, -2, -3, -4, -5, -6, -7. Okay, so there's -5. Let's say we'll indicate that one. And then the y will go 1, and then we'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So there's -17. Okay, so we know that 0 and -17 is a point. -1's at -9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. There's -1, -9. Then at -2, I'm at -5. So -8, 7, 6, and 5. And 2. There's -2 and -5. Then at -3, I'm at -3. So I'm here-ish. Then at -4, I'm at -2. So I'm here-ish. Then at -5, I'm at -1.5. So I'm here-ish. And remember, our horizontal asymptote, sorry, is y equals -1. So I can actually draw that in as sort of a horizontal line here at y equals -1. So we can know that we're approaching that line, and then we're going to drop like so. And then down, we're going to drop even down further down through here, and then it's going to keep going down. So there's my graph. Okay, obviously drawn by hand, it's not perfect, particularly when I'm drawing it with a little tablet and a pen. It's not as easy to do even as doing it on a piece of paper, and that's not as easy to do as doing it graphically, obviously, in terms of using a computer to graph it. So that's the idea behind graphing exponential functions. There's one more example, but the video's gone on long enough, I think, so we'll leave it there, and you can try some on your own.